Today, I'd like to share with you an accumulation of work that's been done by our group over the years, focusing on water for food. We know globally, food security is knocking, or food insecurity, as a matter of fact, knocking every nation's door, including developed nations. And more recently, you see it more vividly because of the disruption in the food supply chain. Water globally is a bottleneck for food security. And the focus of this presentation is to really understand how can we reduce that interdependency of food on water. I'd like to acknowledge the team over the years who have contributed to this work. Some of those are somewhere else at the moment. Some are still at Texas A&M, some are still at Purdue, and some new members are joining the team from the American University in Beirut. So it's really a pleasure to be working with a fantastic team that contributed significantly to this work. Many of you may not be familiar with the American University in Beirut. I'd like to share who we are. I'm not going to spend too much time on the global water and food security issues. I'd like to focus more on the hidden treasures of the soil as an entity that really upholds food security. I'd like to talk about some alternative water potential for satisfying the water demand for agriculture, and hopefully we'll have some conclusions that will be meaningful. The American University of Beirut celebrated 4 years ago its 150th anniversary. It's one of the oldest institutions in the region. Certainly its legacy has contributed significantly to the development of the entire MENA region, and it has also impacted many other parts of the world. Our faculty, the Faculty of Agriculture and Food Science, departments, namely the Department of Agriculture, Department of Food and Nutrition, and the Department of Landscape and Ecosystem Management. There are several cross-cutting programs. Mainly, I'd like to highlight the Food Security Program, which is a cross-cutting program and community development program. Those are cross-cutting, and those are really some of the more common attractions for students across the world. There are several programs that I will not mention here, but some of them will come along in the discussion. I'd like to focus on WAFRA. The Arabic term of WAFRA is abundance, and the philosophy behind establishing this initiative that we launched in 2018 is abundance comes from synergy. And I do truly believe that without the synergy between the primary resources, we will not be able to bridge the resource gap. I will highlight some of the goals for WAFRA, starting with the understanding of the complexity of the system. The water, the energy, the food, the health, which is a focus of our effort here, is very complex, and we need to understand it and kind of unwrap it. More importantly, and this is something that this presentation will highlight, is to reduce the interdependency of these primary resources on each other. Lebanon and the Middle East has gone through several years of drought. If you exclude the last 2 years, we've been going through numerous years of drought. That drought has induced not only water shortage, but has induced food insecurity. So the more we do to reduce that interdependence, the more resilience we achieve in terms of community resilience. Last but not least is to promote One Health, which is the ecosystem and human health and well-being. Those are the goals of WAFRA. We have over 60 researchers involved in 9 different strategic projects working all together at this research facility, which is the ERIC AUB farm that is now transformed into a climate and sustainability center and the hub of the Water, Energy, Food and Health Nexus initiative. Many of you in this room have been involved in this, and I'd like to really acknowledge the Texas A&M Water, Energy, Food Resource Initiative, the WAFNI, that has the goals of expanding the intellectual capacity of the water and energy food nexus in terms of developing analytics, policy, and government best practices, establish a community of science and practice, identify opportunities and gaps in current WAF nexus related research. Here, it's fair to say that Texas A&M was a pioneer in establishing such initiative way before the global community awakened to the importance of this interconnectedness, and I acknowledge the support of all of the units above in establishing that. The most recent activity is that NSF is supported a mega project in this area that looks into the water security in dry areas under water scarcity, focused on the San Antonio River Basin or San Antonio Region L of Texas. The initiative is supported by the Energy Institute that at the moment house this initiative, as well as the colleges of engineering, agriculture, and other units on campus. I also would like to acknowledge the several members that are with us here that have been on the advisory board, including the Bush School of Policy. I will not spend too much time on this, but this is a glimpse of the interconnectedness of these resources, especially geared towards the Middle East, MENA region. I will highlight the challenge of not only the gaps that will exist in the next 20 years in the water, in the food, and the energy, but also I highlight the interconnectedness of these. These are highly interconnected systems, and for that reason, we wanted to understand the complexity and reduce these interdependencies so that we can increase community resilience. The challenges include inequity and in variability in the distribution, the non-sustainable consumption. This is not very much highlighted in many of the literature, but it needs to be highlighted further. The extremes and non-stationarity of the system, and we still do not have the tools to allow us to look into how do we deal with non-stationarity. Last but not least, the business model that I'll talk about towards the end needs to change. The business model in which we manage our water resources, manage our water use as a community is based on an allocation of resources, and that has failed. And we need to realize that we need a different business model. A good example is what's happening now with the conflict in the Nile River Basin, with the dam that's being built in Ethiopia and the implication on downstream community. That model has failed because we have all what we know as of now in terms of the managing water resources is based on an allocative model. And I am calling here to transform that into a synergistic model that allow us to look into a new values or a business model that based on values and not based on the allocation. And again, resilient, sustainable communities is one of the potential that we will like to explore in this. A small pitch on soil. As we all know, soil has been given a very little attention in many of the current projections especially for water. And here I would call for a simple example. All of our soil maps, whether it's an FAO global soil map, whether the US Surgo map or others that we use, they're based on rigid, non-dynamic soil maps based on what I call the DNA of soil, which is the texture. It does not reflect the functionality of the soil. This science is based on 60 years old knowledge, and we know better today to allow us to look at dynamic soil mapping, that the most important part is to look at the functionality of the system. This is important today because the majority of the food we eat, let's take, for example, the wheat. 60%, 62% of the wheat that we consume on our table is done or is produced based on rain-fed agriculture, non-irrigated agriculture. And the core of it is soil. So a better understanding of soil, a new understanding of soil that allow us to dynamically characterize the medium is extremely important. In a nutshell, what I'll be talking about is a new formula for water for food, alternative water sources, and management strategies. We'll talk about water productivity. I'll talk about green water management and accounting. I'll talk about wastewater reuse, and I'll talk about precision irrigation. Those are the pieces of the puzzle that I'd like to together stitch so we come up with a new plan for the future of the interdependencies between water and food. This chart shows the global total consumptive green and blue water use in, we did this study for Northern Africa. The point in this slide is that 60% of the global food production is rain-fed agriculture, and that's green water. 70% of blue water is used for irrigation, and without this is important here, and that's the reflection of the importance of green water. Without blue water, cereal production will only be decreased by 20% because the reliance of cereal production is mainly on green water. What you see in the chart is a rain-fed green water space is much more significant than the irrigated blue space, more important than the irrigated green water. The difference between these two, the blue water is surface water in lakes and rivers, and the green water, or actually the blue water includes also the groundwater pumping. The irrigated green water is what we use for irrigation for irrigated agriculture. What you see here is that, at least for this case study we did in Northern Africa, that the majority of the water, if I call this water pool, is in the green water, much more prominent than combined surface water resources. And that's the resource that has been ignored for many, many years. I can't talk about green water without talking about green water virtual trade. The chart that you see on your left is in fact the tradable green water or the tradable virtual water. Majority of that tradable virtual water is green water. And this is mostly in cereal. And there's a lot of flow that you see, global map, and the importance, the economic importance of green water is very significant to be ignored by us, the science community. For those of us who are not hydrologists, you may be questioning, what is green water? Green water, in simple terms, is the water that's left in the soil after it rains. The question is, and the complexity is, the scientists do not have a unified definition, a quantifiable definition of that green water. Is this the storage? Is it the storage and transpiration? Is this the storage and evapotranspiration? All of these are different definitions. And until we converge, what do we mean by green water? We're still gonna be having challenges in accounting. And I'll come back to this in how we define it in the context of the pedostructure concept later. I made a statement earlier that most of the soil maps are static. And this is what I mean. This is a representation of a soil medium. We started this work back in about 15 years ago when we started looking into how do we characterize the soil medium. And if I look at a soil medium, this is a 3 axes. The plane that is combining axes 1 and 2 is what we call the pedology plane. It's the evolution, it's the natural morphology of the soil material. So this is what commonly known as the pedology, it's the soil science. The vertical plane is what us, the hydrologists, try to quantify these parameters. And we include parameters that has no physical meaning and physical connection to the pedology plane. And this is the disconnect I see. I'll give you one example of this. Most of us are familiar with the representative elementary volume concept, that many of the engineering computation application use the representative elementary volume concept. The problem with that concept in soil science and in soil hydrology, in soil water processes, is what volume you're referring to. The common denominator for a soil is a mass of soil that does not change with time. The volume does shrink, and for those of us who are familiar with Texas soils, the shrinkage can vary between doubling the volume, and that volume, the representative elementary volume, as just one simple concept, does not really fly. Many of us use hydraulic conductivity. You use parameters that are not grounded in the soil pedology. So what we've been working on for the last many years is to bridge the gap between the functionality of the system grounded in the soil mapping. And this is when we come up with the concept of hydrostructural properties of the soil that are looking into grounding the properties with behavior. And this is very important. And this is what was known and what is known as the pedostructure concept. And according to that concept, we have to rederive all of the constitutive equation that relates soil, water with the medium. This is an example of the continuity equation that has to be rederived looking into water content as a kilogram of water per kilogram of soil, and the specific volume, which is the volume of soil over the kilogram of the volume of water over the kilogram mass of soil. So if you look at the independent variable here is not volume, as is traditionally known in most of the constitutive equation in the past. We're rederiving all of the constitutive equation based on a unit mass. The pedostructure characterization lab is designed specifically to characterize the soil according to the concept that was mentioned earlier. And there are two functioning labs. In fact, the third lab was established in Qatar, is not functioning at the moment. There's one in Texas A&M and one at the American University in Beirut here. The lab is to fully characterize a soil based on its unique properties, and the total of 15 parameters. All of these parameters are measured properties in the lab that are verified uniquely in the field. And we could discuss this further, but I don't want to take too much time on this. This is what we call the shrinkage curve. What you see here is an actual measurement of the shrinkage curve, which is the specific volume, the inverse of bulk density. On the y-axis, on the x-axis, you see the water content. If you start at saturation, this is where the medium is fully saturated, and you measure continuously the volume change, the moisture content change. You construct what we know as the shrinkage volume, shrinkage curve. That shrinkage curve has most of the properties we need to characterize a medium uniquely. From interpedal, this is the interpedal, this is what we call gravitational water. And as you see, you go down, the shrinkage is significant after the gravitational water goes away. And then right at this point here is commonly known as what we call the field capacity. For those of you who are familiar with the field, a field capacity is after all the gravitational water is gone, the moisture that is retained by the soil matrix is called field capacity. It's a very useful term, except that it's a very conceptual term. It's a term that up until now was not quantified. And using the pedostructure concept, and I'll show you later on the second derivative or the third derivative of the shrinkage curve of the water pool, allow us to precisely determine that field capacity. And if you continue the journey with the drying cycle, you're gonna reach what we call here the permanent wilting point. That permanent wilting point is at the point where all the water that is accessible for root, for extraction is gone. And beyond that point, the plant will cease to exist. Again, this point, we are exactly able to pinpoint it and be able to quantify it. The importance of these is precision irrigation. Imagine the future when you have access to this curve and you are tracking soil medium from the saturation where you don't need to go there because that's the water, gravitational water that is lost. When I irrigate up until this point without having excess water to be gone into drainage, and I will quantify that and I will trace the shrinkage curve all the way to the permanent wilting point, and I don't want to reach the wilting point, I will irrigate above the wilting point so that the plant is not stressed. This is what I would call the future of irrigation. And this is what I would call how would you really use the most advanced knowledge of our soil physics to allow us to precisely irrigate at the right time and at the right place. This is another representation of what I showed you earlier, except that the water curve, which I call the perostructure water, is exposed to third derivative. And right here, I pinpoint exactly what is the field capacity for this soil, or what's the permanent wilting point for that specific soil. This allows me to do what we call precision irrigation. Combined with other technologies, spatial technology, I would be able to significantly reduce my water use for agriculture. I'm switching to another of those buckets, and I'm gonna call reuse for agriculture. This is a project that we worked on for Tunisia, and this is the wastewater treatment plant right here. And we looked at the system losses within the treatment plant, environmental services. You need to keep water for the environment and water for recharge, industrial water, and there's a bucket here for agricultural use. The problem with this is this system is very complex because there is a social issues that we need to deal with water reuse. There's a soil implication that I'll come back to it. There's a safety, but most importantly, there's a perception. There's a perception that this water is not safe. So the exercise that we did is about feasibility, where we look at all of these dimensions. We need to look at determine the quantity available for agriculture after you take the environmental water, the groundwater recharge, industrial and system losses. We need to map the agriculture demands. This is also important because if you've got a wastewater treatment plant that is too far from the irrigated field, it may be too expensive to pump. So this is the trade-off that we need to look at. And this is where the evaluation of water, energy, food nexus trade-off as a function of the productive use of water. That's an exercise that we conducted, and I'll share with you. This is a map. This is where this green dot is where the treatment plant, and the concentric circles allow us to look at the pumping cost for irrigated agriculture. And this is the trade-off that we're looking at. In terms of water, for this exercise in Gibbs pilot plant in Tunisia, we were able to provide 6.2 million cubic meter per year of water that is made available from that plant for irrigation use. However, the energy, there is a trade-off between the abstraction pumping and trucking that needs to be looked into. And of course, that available water and that available energy allow us to have 3.6 hectares of irrigated crop in addition to what already exists. Those exercises need to be globalized to allow us to look at the potential of reuse. I'm gonna switch now into a very important element for wastewater reuse, which is the impact of wastewater reuse on soil water holding properties. It's seldom that we looked at the long-term impact of soil when it is exposed to different properties of water for irrigation. I'm not gonna go into the details, but all what I can tell you that for this specific case in San Angelo, Texas, where that plot has been irrigated for 10 years, because of the quality, the good quality of the wastewater in that county, and because the groundwater is very salty, we were able actually to show that the irrigation system with wastewater is far better in terms of crop yield and in terms of soil properties than it would be for wastewater reuse. Now, this would not be the case in areas such as Jordan, where we have worked extensively, and in Lebanon, where the wastewater reuse or the wastewater treatment may not be of a good quality, and they will have long-term impact on soil. The point of this slide is reuse is important, but we also need to look at the long-term impact of the ecosystem in which the soil is being exposed to this reuse irrigation. In the introduction, I did talk about a productivity concept, and I did talk about water values. I'd like you to see the figure, the colors here. So I'm gonna take this and switch it in the bottom. I'll come back so this is a conceptual image that we're trying to collect data in our research farm in the Beqa. If I look at the values in which I'd like us to look into a new business model for agriculture, this is the water pools in that order, that in fact this blue water should be up, and it's not in that order. Green water is the big resource that we ignore. How much we can maximize, knowing what we know today about the soil-water interaction, how much green water we can use effectively for agricultural production, using brackish water, using wastewater. Last but not least is using blue water. The reason for that, the agriculture community now is using 2/3 of the global freshwater supply. That is not going to be a luxury for us in the future. We must look at alternative water for continuing the productivity, and we must look at other sources of water where blue water will not be our first choice. The other aspect that I'd like to highlight in this business model, let me switch back this so that you can see the other dimensions I wanted to see. If you look at traditionally today, you look at a farmer in the eye, say, what's your productivity? He will tell you it's tons per hectare, tons of produce per hectare of land. Implicitly, this has no value of the water used for that agricultural production, has no value to the energy, to the air quality, to the impact on soil health, to health risk. That must change. And we must look into not only the biomass per area, we must look into the nutritional value. We must look at a nexus of complexities that exist in the new value-based production system that look into nutrition, that looked into the amount of water footprint, energy footprint, land footprint, health implication on soil health, air quality, water quality. It's not easy, but this is what we need to do. And I would say here, efficiency is necessary, it's not sufficient. This is when it comes to water productivity that we must look at. I was giving a short presentation yesterday. Lebanon exports a lot of potato. It exports a lot of cheap produce, and we don't account for the virtual water that we're losing. So we must look into a productivity issues and the opportunity cost of the virtual water that we're exporting, not only for Lebanon, but many other countries as well. This would be my second to last slide. If I look at what's the importance of alternative water within the SDG context, it addresses, of course, zero hunger. It addresses good health because we're looking into recycling, we're looking into effective and value-based production. Of course, clean water sanitation, no poverty, sustainable cities and communities. This last one is what I referred to by wastewater reuse and looking at the trade-off between pumping and abstraction and whether we can build our wastewater treatment facilities close enough to our production units so that we can fully utilize that reuse. I'm going to conclude with two headings or headlines, one on green water and one on new water. In green water, we need to develop functional definition of green water. We have 5 different definitions now. We need to converge because if we don't define it well, we cannot quantify it. We need to develop a quantitative method for accounting for green water. And this is, I laid out an initial plan for that needs to be further discussed. Develop method for green water, soil, plant, atmosphere continuum at the field and watershed scales. We don't have continuity, a scaling issue that we're dealing with. When it comes to new water, we have non-traditional water for irrigation in arid and semi-arid regions. We discussed several of those new water, gray water, wastewater, and others need to be explored. The safety needs to be looked at, the long-term impact of reuse on health and productivity. Last but not least, we need to have a better understanding of the interlinkages and the trade-off between social, environment, risk, and water allocation strategies. The current business model has failed and will continue to fail, and we need to look at alternatives. I believe this is the end of my presentation. Thank you for your patience, and I hope there was few messages that you were able to take home.